there are only two versions of the solid spherical insulator problems. The problem that we did on our last page of notes where the density throughout is uniform. So if it's a uniform density, then we go right to density equals density, and we solve the problem as we did on our last page of notes. We get our Q enclosed quite readily. What if it is a non-uniform density? Well, if it's a non-uniform density, we can't say density equals density because the density of the entire sphere will not equal the density of our enclosed sphere. So we are again looking to calculate the electric field from r equals 0 to infinity. We are first going to break this up into 0 to capital R. So we put our Gaussian surface anywhere in between. So I have just placed it in here as a representative in between. I've put it, and we will put them always symmetrically into the problem, such that the electric field, we will argue by symmetry, has no reason to be different anywhere on the surface, so it will be constant on the surface of our Gaussian surface, and we will, as you will see in a moment, we'll factor that E out. Well, but first the density. So let's get the Q enclosed. So we're going to address the Q enclosed because that is what we need. Well, if it is a non-uniform density, so non-uniform density, we will always use the calculus version of density. Density equals dq dv. So dv is our volume. The differential volume for a sphere. So this we are just going to memorize or have on our equation sheet, the 4 pi r squared dr. That is the differential volume. So as we increment the dr, we're going to capture all of those 4 pi r squared shells to get the whole volume. So density equals dq dv, and we are told that the density as a function of r equals beta times r, where beta is a constant. So we'll get to that beta value later in the problem. Beta times r, so we are going to bring the dv up. All right, so we're going to bring this dv up here and substitute the 4 pi r squared dr in, so that is our dv. And we're just going to integrate both sides. So let's see what happens when we integrate from 0 to Q enclosed. Let's do it. So when we integrate from 0 to Q enclosed, we are integrating from 0 to little r, where little r is now out to our Gaussian surface. That is important, so we don't go out to the full edge. The Q enclosed is enclosed in our Gaussian surface, so make sure that you leave that as a little r. Very easy integral. The integral of dq is q. There's our Q enclosed. We have an r and r squared, so be a little careful with your algebra. So we get r cubed, integrate, increase, r to the 4th over 4. And voila, we have our Q enclosed to put in. And then we go into showing all our steps mode. Make sure that we have shown the AP grader, right? Our Gaussian surface. Make sure that we have identified the E vector and the n hat vector to show the cosine of 0 degrees. Please do not skip these steps. Put them in. You will lose points for not showing your rationale for why you were doing what you were doing mathematically. The E comes out, and it is a constant by symmetry. The integral of dA is A. So really the Q enclosed, to me, is the difficult part of handling this problem. We get our beta pi r to the 4th on epsilon naught here. So the integral of dA is A, 4 pi r squared. Remember, this is our Gaussian surface. I have all of these Roman numeral 1s in here. That's our Gaussian surface. We lose an r squared. We lose the 4 becomes a 2. So now we get the electric field is beta little r squared on 4 epsilon naught, and that's why we get our quadratic increase in the electric field. So there you have it. Now E max, right, will happen when we capture all of the Q enclosed. So we capture all of the Q enclosed at little r equals capital R, and we are done our calculation for the first part of this problem. Again, the second part, the Q enclosed, is now all of it, so you will definitely see that as a recurring theme. We will not keep showing that result if we have shown it earlier, like we have on page 12 of our notes. So we get 1 on 4 pi epsilon naught capital Q on r squared, just like the point particle, right? KQ on r squared. So we get the 1 on r squared drop off, and you'll notice what's really nice is when little r here equals capital R, we get a convergence, right? So these two values have to be the same. They converge at this single E max point. And if we set them equal to each other, that is how we get our equation or expression for beta. So keep that in mind. The conversion of the two will allow us to determine any constants that are in the problem. So beta equals Q on pi r to the fourth. It also allows us to determine the units, right? Coulombs, meters to the fourth. So all of those would be valid questions that they might ask you on a test. So let me scroll back out here. You can pause the video. Make sure you get all of these annotations into the notes and, of course, ask questions.